Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for MTech EC first semester students. Myself, Dr. Surajit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. In the last class, we have started a baseband receiver with integrate and dump filter. We have calculated peak signal to RMS noise ratio and also calculated probability of error. Today, we are going to start lecture number 2 from the baseband signal receiver and probabilities of bit error with the topic of optimum filter and its transfer function. The lesson objective of this topic is analyze various baseband receivers and compute their probabilities of bit error performances. And this topic is mapped with CO number 5. So let us start lecture number 2 from the baseband signal receiver and probability of bit error with the topic of optimum filter. In case of baseband signal receiver, the signal was passed through a filter, that is integrator, so that at the sampling time, the signal voltage might be emphasized in comparison with the noise voltage. We are now naturally lead to ask whether the integrator is the optimum filter for the purpose of minimizing the probability of error. We shall find that the received signal contemplated in the system of baseband receiver, the integrator is indeed the optimum filter. However, before returning specifically to the integrator receiver, we shall discuss optimum filter more generally. We assume that the received signal is a binary waveform. One binary digit is represented by S1T and other is represented by S2T, and each persists of time t, capital T. The input S1T or S2T is contemplated by noise, Gaussian noise NT. The signal and noise are filtered and then sample at the end of each bit interval, and the output sample is either V0T is either S01T plus N0T or S02T plus N0T. So to minimize the probability of error, one should assume that S1T has been transmitted. if V0t is closer to S01t than S02t. Similarly, we assume S2t has been transmitted. If V0t is closer to S02t than S01t, therefore, there must have a decision boundary, and which is basically the middle level between S01t and S02t. Therefore, we shall take the decision boundary to be, say, V0t equal to S01t plus S02t by 2. This is our decision boundary from from this decision boundary. And now suppose that S01t greater than S02t and S2t was transmitted. Okay. Suppose that, again I am repeating, S01t greater than S02t and S2t was actually transmitted. Now, if at the sampling time, when does the error occur? Then, if at the sampling time, the noise N0t is positive and larger in magnitude, then the voltage difference half into S01t plus S02t minus S02t, an error will have been made. That is, and because we decide that S1t is transmitted rather than S2t, therefore an error has been occurred. So an error will come if N0t greater than or is equal to S01t minus S02t by 2. So S1t is transmitted actually. Rather, in this situation, in this condition, we according to our previous rule, we decide that S1t is transmitted, but actually S2t is transmitted. So hence, the probability of error PE equal to, the limit is this lower limit, this should be the lower limit, and upper limit is infinity. So lower limit is S01t minus S02t by 2 to infinity, and it is the noise, PDF of noise, Gaussian noise, e to the power minus n0 square t by 2 sigma 0 square by root over of 2 pi sigma 0 square into d n0 t. Now again we take that, how to solve the same. Let us consider x equal to n0t by square root of 2 sigma 0. So now after that dx into dn0t and change the limit correspondingly, we get ultimately PE equal to half into 2 by root pi. The limit of integration now S01t minus S02t by 2 root 2 sigma 0 to infinity e to the power minus x square dx. So half 2 by root over pi into this part, that means ERFC part, complementary error function, ERFC, half ERFC into this part S01t minus S02t by 2 root 2 into sigma 0. So this is the error probability of an optimum filter. So optimum filter means you have to minimize this error probability. You are going to minimize. That means the argument term should be maximized. So PE decreases as the difference S01T minus S02T becomes larger, and as the RMS noise voltage sigma 0 becomes smaller. Therefore, optimum filter is the filter which maximizes this ratio. That is gamma equal to S01T minus S02T by sigma 0. So optimum filter is the filter which maximizes gamma. Okay. Now we are going to calculate the transfer function of an optimum filter. Calculation of the optimum filter transfer function HF. We have seen the ability of the receiver to do so depends on how large a particular receiver can make gamma. It is important to note that gamma is proportional not to S1T nor to S2T, but rather to the difference between them. The signal which is relevant in all our error probability calculation is the difference signal. That is Pt equal to S1T minus S2T. Thus, for the purpose of calculating minimum error probability, we shall assume that the input signal to the optimum filter is Pt. The corresponding output signal of the filter is P0T equal to S01T minus S02T. We shall let PF and P0F be the Fourier transform of PT and P0T. And if HF be the transfer function of the filter, then P0F equal to HF into PF. Therefore, P0T equal to minus infinity to plus infinity P0F e to the power j 2 pi ft df. Therefore, HF just PF means HF P0F means just HF PF. So putting the value of P0F, HF PF e to the power j 2 pi ft df. The input noise to the optimum filter is NT. The output noise N0T, which has a power spectral density GN0F and is related to the PST of the input noise GNF by GN0F equal to HF whole square into GNF. Now, using Parseval's theorem, we find that the normalized output noise power, that is the noise variance sigma 0 square, which is basically minus infinity to plus infinity GN0F df. So that is minus infinity to plus infinity HF square GNF df. Therefore, now sigma square equal to P0 square T by sigma 0 square equal to P0 square t. Just put the value of P0 t here and it is squared. See, that is the PT is the input signal power, P0 t is the output signal power, and see here just simply multiplication P0 a Fourier transform. In case of spectrum, Fourier spectrum, P0f is in case of signal power, but in case of noise power, this is HF square because it is a power spectral density. GNF and GN0F is the input and output power spectral density. So in that case, it should be HF square. So now sigma square, that is P0 square T by sigma 0 square, gamma square equal to. Now P0 square T, just put this value from here, that is minus mod square minus infinity to plus infinity HF EF e to the power j 2 pi ft df, and sigma 0 square in the denominator, that comes from this expression, that is minus infinity to plus infinity GNF df. Now how to solve this expression? We can solve this expression using Scrooge inequality. Now what is Scrooge inequality? Scrooge inequality states that given arbitrary complex functions xf and yf have a common variable f, then mod square integrate limit is minus infinity to plus infinity xf yf df square less than or is equal to, in that means total square less than or equal to product of the individual square, that is minus infinity to plus infinity xf square df and minus infinity to plus infinity yf square df. And the equal sign comes when xf equal to k into y star f. Now y star f is the complex conjugate of yf and k is an arbitrary constant. Now using this Scrooge inequality, we can solve this expression. Let us consider, we now apply the Scrooge inequality by making the identification, let's say xf equal to square root of GNF, see, square root of GNF into HF, and YF equal to 1 by root over GNF PF e to the power j 2 pi ft. Therefore, P0 square T by sigma 0 square or gamma square, see the numerator part, that is xf yf integration of xf yf df square, and in the denominator part it is simply just xf square integration of xf square df. So that will be, in the numerator part is, according to this expression, it is less than or equal to product of the individual terms, square of the product of the individual term, and in the denominator already it has xf square, so that part is cancelled, only yf square integration of yf square df, only that part will exist. So gamma square will attain its maximum value when the equal signs may be employed, as is the case when xf equal to k into y star f. Therefore, okay, P0 square T by df yf square, just putting the value of yf, that is P minus infinity to plus infinity, pf square by gnf, and this part e to the power this stuff, that is cos theta plus j sin theta. If you take the mod square, then that part will be 1. So only pf square term exists, and in the denominator it should be gnf df. Okay. And now gamma square will attain its maximum value when xf equal to k into y star f. Now if we follow this term, that is xf into k into y star f, this follow, and put the value of xf into y star f, just complement, that is e to the power minus term here. Then accordingly you can get hf, transfer function hf equal to k into p star f by gnf into e to the power minus j 2 pi ft, and correspondingly the maximum ratio is now, so this is p gamma maxer square, that is p0 square t by sigma 0 square maximum. Now it was less than or equal to, so now it is maximum value is equal to integration of minus infinity to plus infinity pf square gnf df. So this is the transfer function of an optimum filter and the transfer and the maximum value of gamma square. Okay. So let us stop here. In the next class we discussed about matched filter. So thank you.